Consider a system whose state is given in terms of an orthonormal set of 3 vectors. This symbol in quantum mechanics is called ket. It's normally used to represent the state of a system. So this is ket phi. So ket phi 1, ket phi 2, ket phi 3 as ket psi equal square root of 3 over 3 ket phi 1 plus 2 over 3 ket phi 2 plus square root of 2 over 3 ket phi 3. A. Verify that ket psi is normalized by calculating the probability of finding the system in any one of the states, which is ket phi 1, ket phi 2, and ket phi 3, and showing that the total probability is equal to 1. That is part A of the question. Part B of the question, consider now an ensemble of 810 identical systems, each one of them in the state ket psi. If measurements are done on all of them, how many systems will be found in each of the states? Ket phi 1, ket phi 2, and ket phi 3. Now we will start solving the question one by one. First of all, we start with part A. Part A. So now let's write the state of the system. Psi equal square root of 3 over 3 phi 1 plus 2 over 3 phi 2 plus square root of 2 over 3 phi 3. How do we verify that this state is normalized? Because that is what part A of the question is asking us to do. So we are going to verify whether this state is normalized or not. In this case, we are not asked to normalize this state. We've been asked to verify whether it is normalized. The probability of finding the probability Pi of finding a system, of finding the system in state, let's say state Qi, is given by the square of the absolute value of each coefficient. So how do we interpret this? The probability of finding the system in state, let's say phi I, is equal to the square root of the coefficient here. That is what it basically means. So now let's define some terms. So we can say let C1 and P1, C2 and P2, C3 and P3 be the coefficients, the coefficients and probability of finding a system coefficients and probability of finding the system in state phi 1, phi 2, and phi 3. Once we define this whole term here, then our calculation becomes simpler. Now our examiner knows that, respectively, knows that wherever we are talking about C1 and P1, C1 is the coefficient of phi 1 and P1 is the probability of finding the system in phi 1. So we can go ahead and use our defined variables. So now for state psi 1, probability of finding the particle in state 1, in phi 1, will be equal to the absolute square of the coefficient of phi 1, right? And the same thing happened to phi 2, it would be equal to P2, probability of finding the system in phi 2 would be equal to absolute of each coefficient squared. For phi 3, P3 equal squared. So now, what is the coefficient of phi 1? Is square root of 3 over 3. So square root of 3 over 3 absolute squared. What is the coefficient of phi 2? 2 over 3. So absolute 2 over 3 squared. What is the coefficient of phi 3? Square root of 2 over 3 absolute squared. So the absolute sign is telling you that just square whatever is here, and the answer that you get, whether it's negative, you are going to take the positive part. You are going to take it to be positive. So doing so, this one is going to give us 3 on 9, 3 on 9. And this is going to give us 4 on 9, 4 on 9. And this is going to give us 2 on 9. Remember, for the system in state psi to be normalized, the absolute square of all the coefficients should give us 1. So all these are the probability contribution of the given phi 1, phi 2, and phi 3. So this is the probability contribution of phi 1, and this is the probability contribution of phi 2, and this is the probability contribution of phi 3. So the total probability should be equal to 1 if the wave function is normalized. So total probability, let's say PT, total probability, equal to 3 over 9, 3 over 9 plus 4 over 9, 4 over 9 plus 2 over 9, 2 over 9. And let's evaluate this and see what we get. That is equal to 1. So that is it for part 1 of the part A of the question. Once you define your variables, C1 and P2, P1, everything, you define everything, the solution becomes very simple as this. So let's see whether part A of the question is answered. That we should calculate, normalize, we should verify that psi is normalized by calculating the probability and finding the system in any one of the states and showing that the total probability is equal to 1. In this case, we've calculated the probability contribution of each of the phi, and now we add all their contribution and it gives us 1. So that is it for part A of the question. Part 2, part B of the question. Consider now an ensemble of 810 identical systems, each one of them in the state this. Remember, the state was given us in this way. So each of them are in this state psi. So if measurements are done on all of them, how many systems will be found in each of the states. So how many systems will be found in each of the states? Phi 1, phi 2, phi 3. So before we start with this question, what exactly is an ensemble in quantum mechanics? Imagine you prepared 1,000 identical electrons, all in the same quantum state. In this case, all in the same obvious quantum state. You measure the same property. Let's say you measure spin, you measure their spin, all of them. You measure spin on each one of them. So the full set of results from all those electrons is called an ensemble. So 1,000 electrons, you want to measure their spin, so you measure each of them. After that, the result that you get from the 1,000 electrons measuring their spin becomes your ensemble. So now we have 810 identical system, right, or ensemble, and we want to see if we perform a measurement on them, how many of these 810 will fall from each of the phi 1, phi 2, and phi 3. How many will fall from phi 3? How many will fall from phi 2? How many will fall from, will fall on, how do you call it, phi 1? Rather fall on them. So to do this, we need the probability contribution of each of these three set of vectors, phi 1, phi 2, and phi 3. So now, an ensemble of 810. So let's call the total number of ensemble to be 810 to be n. The probability of finding the system in, let's say, state phi is going to give us probability of finding the system in state phi 1 is going to give us n times p1, which is the probability contribution of phi 1 that we calculated here to be 3 on 9. And for phi 2 is going to be n by p2. For phi 3 is going to be n by p3. So what do we get? Our n here is 810. So here is going to be 810 multiplied by the probability contribution of phi 1, which is 3 on 9 here. So 3 on 9, 810 multiplied by P2, which is 4 on 9. So 4 on 9. P3 here, which is 2 on 9. 2 on 9. So how do we get? What do we get? This will give us 270. And this will give us 360. The last one will give us 180. So this means that for our 810 identical system, when we perform measurements, 270 will fall on phi 1, 360 will fall on phi 2, and then 180 of the ensemble will fall on phi 3. So summing all these up, 270 plus 360 plus 180 will give us 810. So after the measurement, this is the number of systems that fall under phi 1, and this is the number of systems that fall under phi 2, and this on phi 3. So let's do a quick summary. The first part of the question asks us to verify whether the state is normalized and show that the total probability equal 1. And we've defined our terms. that C1 should be the coefficient of phi 1, P1 should be the probability contribution of phi 1, and the same to up to phi 3. And now we started our calculation that the probability of finding a state in phi 1 is equal to the coefficient of phi 1 squared, the absolute square. So that is what we did here to get the probability contributions of all the, phi 1, phi 2 to phi 3. And now we now prove that the total probability equal 1. That is for part A of the question. And part B is asking us that an ensemble of 810 measurement were taken, that we should look for to look for how many systems will fall on phi 1, phi 2, and phi 3. And then the formula equal to the number of ensemble multiplied by probability contribution of the vectors, in which we performed our calculations to get the number of ensemble that will fall on each vector. And here state vector, they are state vectors. So that is it for this problem. If you found this video helpful, kindly subscribe to my channel and give a thumbs up to this video for more educational content like this. You can also refer my channel to your friends. Thank you. Bye.